All right, y'all. In this video, we are going to be proving that null spaces are subspaces. Ooh. Okay, so let's first remember what the null space is, and it is solutions to ax equals 0. Okay, and let's remember what a subspace is. And remember, there were three things that we had to check for a subspace. First thing was that 0 is in there. Second thing was it's closed under addition, and it's closed under scalar multiplication. So it has to have the 0 vector, has to be closed under addition, and has to be closed under scalar multiplication. All right. First things first, though, you might have noticed A is an n by n matrix. Null A is a subspace of R. What dimension goes here? It's not just R, because it's vectors. Okay, so A is an m by n matrix. All right. And things in the null space are solutions to this equation. I have to be able to multiply them by A, which means that that had better be a vector in Rn. So null space Rn. Yep, great. All right, let's go ahead and prove this. So first thing we're going to do is check is a 0 in the null space. Well, how do we show something is in the null space? Okay. To show U is in null A. Show that it fits that equation, that when you do A times U, you get 0. So just put that in a little box. We're going to be using that a lot in this theorem, in this proof rather. Okay, so we need to show if we multiply A by the 0 vector, well, what do we get? We get the 0 vector. That's exactly what we want. All we're saying here is the trivial solution is always a solution to the homogeneous equation. So we're good. 0 is in the null space. All right. Next thing we want to do is show that null space of A is closed under addition. And remember, we talked about this a little in the last section, but you got to start with generic U and V in the null space, and we need to show that U plus V is also in the null space. And remember, you get in the null space by showing that if I multiply U by A, you give me 0. So what we're trying to show here is that if I do A times U plus V, I want to end up with 0. Okay, so I'm going to start with exactly that. Y'all, I love this proof so much. It's so great. Okay, so now if we were in class, I would ask you, okay, well, what can I do next? And even if you don't know what is happening, if I give you something that looks like this, right, distributing is an option. So we're going to do that. Okay, A times U plus A times V. And now there's not a ton that we can do, but we know that U and V are in the null space. And what does that mean? That means A times U gives us a 0, and A times V gives us 0. That's the definition of the null space. Anything in the null space, multiply it by A, zeros it out. So that means that this is 0, and this is 0. That's very convenient, because what happens when you add the 0 vector to itself? You get the 0 vector. So it is closed under addition. All right. Now, what we want to do is we need to show that the null space of A is closed under scalar multiplication. So just like last time we started with generic stuff, we need to start with generic stuff here. We're going to start with a generic scalars. We're always going to assume are real numbers, and we're going to start with a generic U in the null space. And again, what we want to show, we have to show that C times U is in the null space. And what does that mean? How do you get in the null space? We need to show that when we multiply it by A, that ends up being the 0 vector. Okay. So we multiply it by A, and you may or may not remember that matrix multiplication and scalar multiplication are really nice. What we can do is sort of bring the A through the scalar multiplication and do the matrix multiplication first and then scale on the outside. But let's remember, what do we know about U? It's in the null space. And if it's in the null space, then A zeroes it out. So this part is 0. What happens when we scale the 0 vector by anything? We get the 0 vector. So this is closed under scalar multiplication. Joy. Therefore, the null space is a subspace. And it has to be a subspace of Rn, because if it's not n, then multiplication doesn't make sense. And we get to draw our little proof box, and we're done.